Um, so the log, the serial log was an optimization to make to increase the speed of commits, even though it adds extra writes to the overall processing. Falcon is also a more recent design, although of course everybody is moving in this direction. And as Jim explained this morning, it has a separate record and page cache. It's also by the time Falcon was designed, it was perfectly clear that there were going to be parallel threads, and increasingly so, and that we wanted to do multi-threading not only at the connection query level, but within connections and queries. So there are different thread banks for doing different operations, and they all share common data structures, and a lot of thought has gone into the synchronization primitives necessary. Both Falcon and InnoDB default to repeatable read. Repeatable read is defined in ANSI as I describe it here. Repeatable read in the standard says that a single transaction which executes the same query over and over will get the same results, except that you'll see results that have been committed between the two runs. Both InnoDB and Falcon have a repeatable read that is consistent. You do the same select, you get the same results until you commit and get a new snapshot of the database. And here I go. The purpose of this slide is to say the better you know InnoDB, the less you're going to like Falcon. The more you know of one database, the better you are at finding the best way to code your application in that database, the harder it is to go to another database. People occasionally ask, well, how hard is it going to be to convert my application from InnoDB to Falcon? And I try to say, don't do it. There's no reason. They're both part of the MySQL family. If you have an application that's running in InnoDB and you like it, fine. If you're thinking of a new application, then you might look at both. And the quirks that I'm going to talk about are oddities in the way the two repeatable reads work. And the first example is one that has been in Falcon. It was in Jim's previous databases. And essentially, you have one table, it has one field, and that field should contain a count of the number of records. In Falcon, you insert into it, select count from it. You're the first one in, that's no problem. You count 0, you store 0. The second transaction, because the first transaction hasn't committed, the second transaction looks and sees no records, it also stores 0. And if you repeat the two of them and then commit, you end up with a table like this, which is nothing that you could ever get with serialized transactions. But this transaction sees first no records and the one record it stores, and the other transaction sees first no records and the first one record it stored. In the same case, InnoDB puts a lock that causes the second transaction to wait. Its insert does not happen until the first transaction has committed. So the result, when you're done, is what you would get with serialized transactions. That is, there's a 1, a 2, a 3, and a 4. However, the second transaction says select star from table, it gets 0. It says insert into table, count of table, and if it looks at the table then it sees probably in this case a 2. So what the InnoDB designers have done is to favor serializable results over repeatable reads. And Falcon favors repeatable reads over serializable results. Slightly related is this work where, and I'll go to the example, you have 2 tables. One of them is dinner menus and one of them is lunch menus. And somebody says, okay, in this restaurant, the dinner menu will be twice the price of the lunch menu. And unfortunately, he says it's 2 different people, and each of them goes to make the change. The first transaction says, okay, I'm going to set the lunch to half of dinner. And the second says, I'm going to set the dinner, I'm sorry, I've got that should be a ×2 and not a ×0.05. I'm going to set the dinner to twice lunch. The result is that lunch ends up being $12.50 and dinner ends up being $10, which was not at all what was intended. So this is the result of that particular. Each query wrote down what it saw, and the result was not what was expected in the case where 2 of them were running together. In InnoDB, transaction 2 waits for transaction 1 to commit and then gets the correct result. Looking at it from a different side, in InnoDB, a select for update can see a different result from a normal select. If a concurrent transaction has modified and committed a change to this row, the select will see the consistent result, and the select for update will see the most currently committed result. In working on the DBG2 numbers, we decided that it would be worthwhile to have a Falcon mode that does the same thing. By default, Falcon will, in its consistent read, Falcon will get the consistent value each time. If you have consistent read off, Falcon will get the most recent committed record when it says select for update. The other thing that surprised me when I was beginning to look at it is that InnoDB does an implicit select for update in some queries. In the same case where you have a table where when your transaction started the value was 1, someone has changed the value and committed the change. If you do a create table as select from T1, you get the most recent committed value and not the original value. So these are oddities which are fairly, yes?
Okay, the reason why InnoDB locks the select table is that the operation has to be serializable for MySQL's
Yes,
statement level replication.
For statement level replication, if you don't do this, you don't get consistent slaves. And that is a barrier that Falcon has yet, as of the moment, Falcon only works with row level replication to avoid exactly that problem. And I'm not saying, don't misunderstand. Neither of these is more right or more wrong. It's just that they're different. And as you're looking at, the better you understand InnoDB, the more surprising you're going to find Falcon, and probably vice versa. And as an introduction, because Kevin is going to be talking a lot about the various changes that we've made to improve performance, and I promised to give a quick introduction to what we call the front end and the back end of Falcon. The back end doesn't have tail feathers, the front end doesn't have a beak. The front end is the part that runs user queries, returns results, and provides commit durability. The back end is the part that turns that into a consistent on-disk database. Essentially, you start with the on-disk database, which are table files, I/O threads read it into a page cache. The page cache puts the active records into a record cache. From that point, most operations will happen between the record cache and the serial log. Changes get made into the record cache. On commit, they go to the serial log. And that is the high latency part, the low latency part of Falcon. Eventually, the changes in the serial log if there's idle time, during idle time, the changes that are written to the serial log and are on disk get moved by a bunch of threads. Both the light blues are threads. The Gopher threads take the changes from the serial log and move them onto database pages in the page cache, and the I/O threads move them to table space files. So when Kevin talks about what's happening in the back end, it is taking blocks of changes from the serial log and normalizing them into pages and pushing them out to the table space files. And so it is.
Okay, thanks.
No, you're not fine.
This little point. What I'm going to try to do is, turn it down a little bit. I'm going to try to go over some of the kind of the saga or of trying to improve the performance of Falcon over the last 6 to 9 months. This is inter-to-be performance today. And I'm putting that up there because every time we run a comparison, we get different numbers, slightly different settings, slightly different computers or something. It's really strange sometimes. And but we want to just compare against what, to put the bar as high as we can and try to reach it. This chart was done back in February, and typically starting back in summer and last fall, we were from various tests, 30 to 50 to 70% of InterDB's performance. So we had a lot of things to improve. Go through a few of the problems. First, we noticed that the sweet spot for Falcon should be small transactions, and we noticed that it wasn't at the performance that we wanted it to be. So we narrowed that down to how too much serialization in starting up a brand new transaction. We did several things to fix that. We noticed that a lot of the transactions objects that are reused are only used for read-only transactions, just a query. And when the commit happens at the end of that, it's just the transaction object is not needed anymore. So it can go back onto a separate list and be reused without having to do an exclusive lock. And then we added, we found too much serialization in starting up a brand new transaction. And actually, we found these results January this year, and we implemented them in February. And then there was an issue with the scavenger. The scavenger thread, it's a background thread, but it cleans up the record cache of records that don't need to be there anymore. And it was grabbing a lock on the table and holding it while it was searching for records to be scavenged. So we reduced that so that it only holds the exclusive block when after it has found the records it's going to scavenge, then it gets a quick exclusive block and gets rid of those records. So that helped the performance on the front end. But then we noticed a really strange thing. We found that there was while we were running DBT2 tests, we ran a monitoring thread that would just keep asking the Falcon engine about its memory, all its memory objects. What do you have allocated? Just go through all your memory objects, add them all up, and put out a report into an information schema. This should have really slowed things down, but what we found was that it sped things up. And so this, we were just stoked for this for for a long time. Finally, we found out that what was happening was that there was a log jam of transactions that had been committed, put into the serial log, and not processed by the Gopher threads into the page cache. So this log jam was getting bigger and bigger, and it became harder and harder for the foreground threads to get work done. The latency was backing up. And the monitoring thread just slowed down the front end. And so things could go smoothly. The log jam wasn't as big, and things went faster. So first thing we did was we put a limit ourselves. Just say, only so many logs in the river before the log jam. So it was a limit on the number of active transactions that could be committed at one point in time without having been completed into the page cache. And then the second thing we did was, okay, let's increase the performance of the back end. So there's two parts of the back end. The first, the upper part is getting committed changes from the serial log into the page cache. That's done by, well, as of last summer, the Gopher thread. And so the first thing we did was add a whole pool of Gopher threads. We call them a herd of Gophers. And it turns out that herding Gophers is not that easy. You have to think about it, there could be a very large transaction that updates a record, and then followed by a very small transaction that updates the same record. Now, if these herd of Gophers all come in, the first one grabs the big transaction, and the second one grabs the little bitty transaction, the second Gopher can get finished and update the page for that record before the other Gopher finishes that large transaction. So when the first Gopher thread finally gets to that record, and he looks at the page and says, wait a minute, there's a newer record on that page than what I'm about to write to it. So we had to prevent that. Now, on the real back end, that's where we had the most to improve. We had one I/O thread, so we added a pool of I/O threads. And then instead of using buffered I/O from the operating system, we went with direct I/O using the ODirect flag. And in order to make that efficient, we had to consolidate the pages that were written consecutively on disk. So we write more than just one page at a time, but a whole bunch of pages at a time with direct I/O. Now we've got a whole bunch of I/O threads writing larger chunks, and then there became a problem in that these I/O threads would kind of overlap. They had exclusive access to the file while they're writing these larger chunks. And the poor client threads are trying to do a read of a single page. You can't get in there because the checkpoint is happening with a bunch of I/O threads. So we had to add prioritization of these I/O threads so that the read threads, client read threads, they're higher priority. They can get in, get their read, and the latency, which is the most important thing. Query latency could be better. So we always knew that index pages needed to be done more efficiently. A Falcon index page is each index entry is encoded and prefix compressed so that it's variable length, and then we only store what's different from the previous keynote. So you have a whole lot of stuff on the same key page. But because of prefix compression, the only way to find something within a key page is to start from the beginning where you know the entire key and then step through all the keys. And when you do some profiling, you can see, we could see that it was using about 10%, or it just depends on the test. It was using too much time traversing the key page, trying to find the right key on the page. There was a section of the key page set aside for vectors or offsets into the page, and we implemented that just recently, and got that in. That's not in the 604 release which is out there, but it's in the 605 release coming out soon. And we call these the super nodes. That means that the offset at the beginning of the page goes directly to a key node that is fully uncompressed, so you can know what the whole thing is. So there's only 16 offsets, and we can do a quick binary search, get to the correct 1/16th of the page, and the whole search of the index page is an order of magnitude faster. This was really interesting. We found very inconsistent results in our DB2 testing, which is very frustrating because you run the same test 3 times, and the standard deviation between the three different runs, same machine, same settings, everything would be entirely too high. So something is going on to make this inconsistent. We worked pretty hard to try to figure this out, and we finally discovered that there was a problem in the way that threads wait for another thread to signal. We have sync objects that protect various data objects and sections of code, and if you're waiting on a sync object, there's a gap in there where you could miss the signal, and so there was a portion in there where we were not holding a mutex. So we extended that holding of that mutex until from the lock attempt right until we're just barely ready to go to sleep. Then we release the mutex, and then because we're holding it during that time, we're getting signal reliably, and so we don't have these what we call thread stalls. When the threads go to sleep, the maximum that they'll sleep for was 10 seconds. But if you're waiting on some particular sync object and you miss the signal, some other thread might go back within that 10 seconds and get the lock on that object, and then release it and signal you. So your stalls are anywhere from a microsecond to up to 10 seconds. But if you get a whole bunch of these things, then they can the performance just is really strange. It's just unreliable. So here is here's some results for well, this is where we were. The bottom line, the red line, was measured in February, and we typically would run lower performance. The top line is the blue line, is InterDB's performance as of yesterday with the best tuning settings that we could get for the machine we measured and so on. And then there's the Falcon line as of last week. So we have, this Falcon line reflects the change I just talked about with the stalled threads, avoiding having thread stalls.
Could you explain the axes?
Yeah. So this is, on the left is transactions per minute, new order transactions per minute within the DB2 run. It's not the full number of transactions, but particularly new order transactions per minute. And this is 8 clients, 16, all the way up to 128 clients. So as you go to the right, it's more concurrency. This is the last one was on a machine in which the database wasn't that big, and we had plenty of cache. It was fully cached. This is a 9 gigabyte database on a 16-way or 8-way computer. Plenty of memory, but we only used 2 gigabytes of cache. So we have a 9 gigabyte database, 2 gig of cache. So we have a lot more. The I/O comes more into effect here. And this is where we are currently trying to focus our efforts on performance. This is the InterDB's number as of February. This is the best number I could get for them. They have a drop in a higher level of concurrency, but I wouldn't count on that staying there.
No. We hope and expect that it will not stay there.
Yeah. So that is not our target. This doesn't thrill us. This is our target up here. So and we want to continue this. this up and to the right as we get more. This is 192 concurrent clients. As we get more 256, 512, we want to continue going up to the right. Yes?
Was the footprint on this the same for the two engines, or were you significantly smaller or larger?
I don't know the answer to that.
That's a big issue when you're only talking about 9 gig versus 2 gig.
Yes. There's a lot to look at there. This shows the effect of thread stalls. The higher concurrency you have, the more threads are beating up against each other, and the more the threads are waiting on each other, the more chances you get of thread stalls. So this is a couple of different runs that we got between this run. This was in December. These two were in February. And what we had done, you can see we had a little bit of better performance because we had added a performance improvement with transaction starts. I mentioned that earlier in the talk about how we can get more transactions to get started quicker, so the theoretical latency on the front side is smooth. And what that gave us a good start, but then we started getting thread stalls. And if there were no thread stalls, we would continue right on up. But these thread stalls just screwed everything up. Now, in March, we ran against off the main tree, and it had the same code in, and it had these thread stalls, but it just didn't happen to the thread stall. So this is our target. This is really where we think we were without these problems. And it's really strange how sometimes the timing of these machines is just you don't see the problems, and other times you do. So this is really where we were as of March. So we fixed the problem with the thread stalls, and we found a problem that caused some crashes. We needed an extra synchronization object. One, we were traversing prior records in the record cache. So there was some things going on in there. We were getting some records going away while there's still a pointer to it. So we added a new sync object. And look what we did. So this gives you an example of the frustrations we have as trying to improve the performance of Falcon. Is a complex engine like this. It takes 2 steps forward and 1 step back, and then so we're going to take another look at these synchronization objects for this. We can see if we can clean it up, hold it less often, and there's just lots of other things we can do. We're just going to keep moving it up and up. Mostly these charts show that we have a lot of work to do on the back end, the idle threads, getting pages down to disk. And this test, let me say, the DBD2 test is 40% writing to the disk. So it's how many threads can throw data onto disk as fast as possible. That's not where Falcon is targeted, but that's what we're trying to improve. In these high update tests, we've discovered that the balance between the page cache and the record cache is not what we expected. If you make a bigger page cache and a smaller record cache, these tests run a little bit better. But if you've got a read-only type environment, you might want to balance it differently. So your results may differ from this, but this is what we're finding for a highly concurrent update test, is that this is a particular test in which we have these two numbers, the record cache and the page cache, add up to 2 gigabytes. The database is 9 gigabytes. And we tried different variations. And the best one was with a larger page cache. Our best results are using about a 2 gigabyte record cache, and then varying the page cache depending on your concurrency, how much you're writing. We are trying to put the current release up onto this site, Falcon Feature Preview on the Forge, and as soon as we release 6.05, not release, as soon as we get get that built and we'll start testing it. We'll put it up here so you guys can test it as well. Okay. Any questions? Yes.
How many threads do you create?
We create on the front. Well, you can choose how many Gopher threads. You can choose how many IO threads. By default, I think it's 5 each. And on the front end, these threads come in from MySQL. I don't know what I think they're.
Well, I was asking about the Gopher knife.
Yeah, so the background threads, you can control that with a step. Any more questions? Yeah.
Can you explain why Falcon got different results from NODB in this first case? Or what is it about the Falcon that's different that caused different answers?
The question was, why do we get different answers? And the answer is that Falcon is providing a completely repeatable read, that is, it is ignoring subsequent updates. And in some cases, to produce serializable results, NODB is reading the most currently committed result rather than the result which was consistent with the start time of the transaction.
So within a single transaction, 2 reads, let's see, repeatable with Falcon, but how is NODB?
If you use a select for update, that's true. And in the case where the select is in a subquery that drives an insert or an update. Is that true? And the reason for that is that statement-based replication doesn't work at all if you don't do that. Or it works, but doesn't provide a slave that has the same content as, which is not what you want.
Does that explain the first 2 quirks that you described as well?
Yes, that Falcon's choice in that case means that each transaction sees its own view of the database and is unaware of changes by other transactions. So in the case where you're trying to store the count in a single table, each transaction sees only its own results. So it sees 0 and 1, and then the other one sees 0 and 1. Although, in fact, when both commit, there will be 4 records in the table.
I'm sorry, I don't mean to monopolize, but just to follow on that one. It seems like the problem isn't what it's reading, but what it's preventing, that prevents an insert without the insert.
I'm sorry.
It seems, again, don't want to monopolize, but it seems like the issue isn't what the difference in what they read, but that NODB prevents the insert of the count, and Falcon doesn't.
That's not, in a truly serializable system, one of those transactions would get, I believe one of those transactions would get an error so that it couldn't, in the case, I find it anomalous that in that case, if you ask NODB, select count of table, it tells you 0 or 1. And yet, when it does an insert into the table of the count, it puts in 2 or 3. So if you select from the table, you get 2 and 3, although the count is supposed to be 2. And the question is, in Falcon, if you say, okay, how many records are there? There are no records. I store a 0, and it tells me I've got 1 record, and so the view of the table and what it's storing are consistent, and the result when you're done isn't. It's not something that people ordinarily do, and most people who care about this sort of thing would put a unique index on that table, and the problem goes away. It's just an anomaly of the two implementations. Yes, sir.
Oh, okay. If, say, my husband and I were trying to take money out of our bank account at the same time, and the database said this was based on Falcon, what would we see as we're trying to do this? How would that work?
You would ask how much is in my account. He would ask how much is in the account. He'd get the same amount. So you would take out yours and you complete it, and he would say, okay, take out some money, and his would fail because the record changed while his consistent read transaction was active, and so he wouldn't be able to update the record.
But if you think you refresh the page or something, well,
No, it does handle that.
take it out,
Yeah, well, that transaction would fail. Then you say, okay, read again, and then it would see your value.
and then it would be, okay.
I want to point out that these are two methods of doing repeatable read transaction. And in Falcon, you choose repeatable read, but then you also have to choose, there's a setting called Falcon consistent read. Consistent read.
Yeah.
And that's normally on, which means we get a very consistent repeatable read. But you can turn it off and act more like repeatable read.
But not exactly like it.
Not exactly.
Let me see if I can clarify this slightly. If Falcon has consistent read turned off, both Falcon and NODB can get different answers when doing a select from table and when doing a select from table for update. Each system, when they see an uncommitted record, when they're doing a select for update, will wait for that record to be committed, and then they will see it. So you really have different record visibility rules. When Falcon is running in its default consistent read mode, it will always see a consistent view of the database at the time that that transaction started. If another record is modified, it will not see the change. It won't wait for it. And what happens in that mode, which is Falcon consistent read, is that if you try and modify a record or do that you didn't read, or even do a select for update for a record that wasn't visible to you, you will get an update conflict and the transaction will fail. So it's a trade-off. Do you want to wait for the other transaction, even if the record visibility rules are flaky, or do you want to get a proper, intellectually defensible result, but your transaction doesn't work? So, kind of damned if you do and damned if you don't, and you can flip your coin and decide which one you like better. Is that completely murky?
Yeah. Any other? Yes.
So how do you back it up? Does it just back up what's written in this? Does it back up the log? And also, how do you recover in the case of a crash?
Okay. I assume you just mean Falcon because I haven't a clue. With the new backup, what's currently available is a logical backup, which is a snapshot of the database as of the time that the backup started. And sometime over the next month or two, we will have a fast backup that doesn't go record by record, but gives you a compressible snapshot of the database. Now, in terms of recovery, if you have a crash and you've got a lot of transactions that are in the serial log that haven't been moved, then the first thing when the system starts up, it discovers that it has a serial log that has active records in it, and it processes those records and applies them to the database before you start.
Thank you.
Yes?
I felt like the serial log was not being written to disk in time before.
The serial log is written. The serial log is written to disk before the commit returns success to a transaction. Commits are grouped. You have a first transaction that commits. The serial log goes off to do its write. Other transactions are added to the serial log while that write is in progress. All of the ones that are there get written in the next cycle. So a single cycle, a single write can write multiple transactions. There's no wait. If there's somebody waiting to commit, you start another write as soon as the first one commits. But the serial log is in fact flushed to disk before the commit returns, any commit returns success.
The Gopher threads don't have to read back from that serial log directly because we have these large windows into the serial log. What's been written recently is still a window. There's lots of windows. You can set that up to 100 or more, and that's what we do when we do this test. We have 100, and these are 1 meg windows in the serial log.
Any other? Thank you very much.